Hello, everybody. Good morning. We had a really hard time with the title this time. We had to change it a couple of times, but we stuck with generics. We've all been waiting for this moment for some time now, with excitement or perhaps with trepidation. But that moment has come. Generics will officially be part of the language, starting with Go 118, released for schedule sometime next February. We have talked about generics at past GopherCons. Last year we presented a detailed design. We had a working prototype implementation. We had finalized the syntax. We had figured out how to represent constraints as interfaces. And we had a working type inference. But there were a few things that we were not entirely happy with. In the meantime, I think we have figured out these last issues. I'm personally very happy with where we arrived. We have a design that is pretty clean. It is 100% backward compatible with existing programs, and it has some room to grow. And most importantly, there is still a feel of this is Go. So what exactly is new? If you look at the step back a little bit and look from a 30,000 feet point of view, there's really just three things. And those three things are obviously type parameters for functions and types. These are the visible signs of genericity. And then there's a new, different view of interfaces. They are now not just able to define sets of methods, but also sets of types. And finally, type inference, which hopefully should smoothen out the generic code a little bit and make it a little bit more lightweight. I'm going to cover briefly each of these topics to give you kind of a flavor of the things to come. So let's start with type parameters. A type parameter gives you the ability to parameterize a function or a type with types. A type parameter list looks very much like an ordinary parameter list, except that we use square brackets instead of parentheses. I'm going to show you a couple of examples to show you how this works out in practice. So this is your generic min function that you've seen probably many times, probably written a gazillion of times, and hopefully we don't have to write it anymore in the future. We can make this function generic by replacing our float64 type with a type parameter, in this case t. And because we have a new type t here, we also have to declare it, and that happens in this type parameter list, which is marked here in red. When we want to use this min function for int arguments, we have to call it, of course, with our int arguments, but we also have to provide the respective type, which is int in this case. Providing this type argument to the function is called instantiation. That's a fairly important part in generic programming. Instantiation happens in two steps. First, all the provided type arguments are substituted for their respective type parameters. And then in a second step, after substitution has happened, the compiler checks that each type argument implements its respective constraint. And what that exactly means, I'll go into it a little bit later. But if instantiation fails, or I should say if that second step fails, then instantiation fails, and in this case, your program is not going to be valid. So going back to our original example, we can instantiate this generic min function just by itself without actually calling it like this. We provide a float64 type argument to min, and then we get a non-generic min function, which is essentially our original min function. And we can then call it like any ordinary function. And just how to see how this looks for types, because we can parameterize types, of course, as well. Here's an example of a generic binary tree. And here the data type is generic. We use a type parameter t again. And we can now create an instance of a string tree, for instance, by instantiating this generic tree with the string type. We can also have methods on generic types. I'm not going to go into details here. So let's talk a little bit about the kind of types that a type parameter can be instantiated with. Let's talk about type sets. So an ordinary parameter list has a type for each parameter. So in this case, we have the type is float64. And this type actually tells us what kind of values are valid as arguments for x and y. So this float64 type is a set of values. Now, in type parameter lists, each type parameter also has a type. And this type is kind of a meta type, and it tells us what kind of types are valid for this type parameter. So this meta type actually defines sets of types, and we call this a type constraint. Now, in our generic min function, the type constraint is imported from the constraints package. This is a new package in our standard library. And here, the ordered constraint describes the set of all types with values that can be ordered in some ways. And in our case, they can be compared with the less than operator. And the constraint ensures that only types with orderable values can be passed as arguments to this type parameter. And it also tells the min function that within its body, operators of types that are of this type parameter t can be, operands of that type parameter t can be used with the less than operator. In Go, constraints must be interfaces. Interfaces define methods, and so it's obvious that we will be able to define type constraints that require certain methods to be present. But constraints ordered is an interface too, and the less than operator is not a method. So how does that work? So until recently in the Go spec, an interface defined a set of methods. If we have an interface with methods A, B, C, then we say that the interface has a method set with the methods A, B, and C, and every type that implements those methods actually implements that interface. But there's a different view. We could look at the set of types that implement those methods and then say that the interface actually defines that set of type. Now, each type that is an element of this type set implements that interface. And it's pretty obvious that these two views are essentially identical. I mean, for each set of methods, we can imagine this typically infinite set of types. And now we're just saying the interface defines that infinite set of types. And if we want to check if a type implements the interface, we just check whether that type is an element of that set of types. But this view as a type set has some advantages because we can now control it in new and different ways. For instance, we can add types explicitly to the set. And in order to make this happen, we have extended the syntax for interfaces exactly to be able to add additional types. For instance, here we have an example of an interface with 3 types, int, string, and bool. And this interface defines the set of exactly those 3 types. Or another way of saying this is that these 3 types implement this interface. Now, if we're going to go back to our previous example, remember the constraints.ordered interface. This is the declaration of that interface. Here, this declaration states that ordered is the set of all integer, floating point, and string types. The vertical bar expresses a union of these types, or in this case, type sets. And integer and float are interfaces that define type sets themselves. They are similarly defined in the same package. Note that there are no methods on this interface. Usually, we do not care about a specific type. Like, we don't want to have a set that just contains the int or string type. We care usually about all the string types and all the int types. And that is what this new token tilde is for. Tilde string, in this case, denotes the set of types that consists of all types whose underlying type is string, or all string types. So of course, with Go 118, we'll still want to be able to specify methods. And so we'll still be able to do that, of course, in interfaces. And we can embed other interfaces as usual. but we will also be able to embed arbitrary types and unions of this form and tilde type elements. Now, used as a constraint, the typeset defined by a constraint interface defines exactly the type arguments that are permissible as arguments for the respective type parameter. And within a generic function, for operands of type parameter type, only the operations that are permitted for all the types in the respective typeset are permitted on those operands. Interfaces used as constraints may be given names such as constraints.ordered, or they may be used directly inline inside the type parameter list. For instance, here we have a type parameter list that declares two type parameters S and E, which might be written like this. So here S is a type parameter that requires a slice type, an arbitrary slice type whose element type is not further constrained. This is a fairly common scenario. And because it is so common, we've introduced some syntactic sugar that allows us to leave away, or actually we've removed some syntactic sugar, I should say, that allows us to leave away the interface curly braces around it. And we can just write the second line, as I've shown here. And finally, because the empty interface appears quite often in type parameter lists, and for that matter in Go code, we introduced a new pre-declared identifier, any, that is an alias for the empty interface. And so this, any identifier can be used anywhere instead of the empty interface. Interfaces that define typesets are a powerful new construct. They really make constraints work in Go. But for now, such interfaces may only be used inside type parameter lists in constraint position. But it's not hard to see how such interfaces might be useful in general for arbitrary variables. And maybe that is something that we will do in the future. And I think there is an issue for that. So finally, the last but not least new mechanism, it's type inference. I'm only going to touch very briefly on this. Going back to our original example, with type parameters comes the need to pass type arguments, which can make for rather verbose code. And frequently these type arguments, they can actually be deduced from the ordinary parameters that are arguments that are passed in a function call. So here we have our generic min function again. We pass two arguments A and P of type float64. And by comparing those types against the parameter types, here there's only one, T. So by comparing T against float64, we can infer that the type for T actually must be float64. This is what the compiler does. And if it can do that successfully, then we can simply leave away the type argument, which leads to a function call for min that looks like any ordinary function call, no type parameters or anything. Now, the exact details of type inference are pretty complicated, but using it is not. Type inference either succeeds or it fails. If it succeeds, type parameters can be left away, and all is good. The generic function call looks like any ordinary function call. If it fails, then the compiler will complain, and we simply provide those type arguments. Now, we have tried to strike a balance between the complexity and inference power for type inference, and we probably haven't gotten it quite right. And so there's some room to fine-tune and refine over time. The effect will be that more programs won't need type arguments. But the important point is that programs that don't need type arguments today, they won't need type arguments tomorrow. That's really it. 3 major new things in Go: type parameters for functions and types, a more powerful form of interface types to express constraints, and type inference to smoothen out programming generic code. Thank you very much. I'm going to hand it over now to Ian Lance-Taylor, who will go a little bit more in detail with type inference and how to use generics in Go. Thank you very much. Thanks.
Thanks, Robert. Thanks for that great description of generics as they're going to come into Go 118. So I'm going to start by describing a particular kind of type inference, which we call constraint type inference. So I'm going to start with an example. Suppose we want to scale a slice of integers, returning a new slice in which each element has been multiplied by some value. We don't care what the exact type of integers are in the slice, so it's easy to write a generic function for this, similar to the ones that Robert showed earlier. But there is a problem with this particular definition, which I will explain as we go along. Now, continuing the example, suppose we have a multidimensional point type, where each point is simply a list of integers, giving the coordinates of the point. Naturally, our type has methods. For the purposes of this example, the details aren't really important. Sometimes we want to scale a point. Since a point is just a slice of integers, we can just use the scale function that we wrote earlier. Unfortunately, this doesn't work. We got a compilation error, which you can see on the screen here. What went wrong? The problem is that the scale function returns a value of type slice of e, where e is the element type of the argument slice. When we call scale with a value of type point, whose underlying type is slice of int32, we get back a value of type slice of int32, not a value of type point. And of course, value of type slice int32 does not have any methods. So this all follows from the way that generics work. But for an example like this, it's not what we want. In order to fix this, we have to change the scale function. The changes are highlighted in red here. We've introduced a new type parameter, s. That's the type of the argument. We've constrained that type parameter s so that the underlying type of its argument must be a slice of some element type e. So the first argument to the function, the first regular argument, is now type s rather than slice of e. And the result type is also now slice of s, is now just plain s. Since e is constrained to be an integer, the effect is the same as before. The first argument has to be a slice of some integer type. The only change to the body of the function is that now we pass s rather than slice of e when we call the make function. This new function acts the same as before if we call it with a plain slice. But if we call it with the type point, we now get back a value of type point, and that's exactly what we want. But it's fair to ask, and here we're going to get into the inference part of the talk, why is it OK to write the call to scale without passing explicit type arguments, as shown in the comment there? The new scale function has two type parameters, s and e. In a call to scale where we don't specify any type arguments, function argument type inference that Robert described lets the compiler infer that the type argument for s is point, as Robert showed us. But the function also has a type parameter e, and we need to have a type argument for that type parameter. The process by which the compiler can infer that the type argument for e is the element type of the slice is what we call constraint type inference. The exact definition of constraint type inference can be found in the language spec, or rather it can soon be found there. It's not quite ready yet, but soon. There is a description in the generics proposal, which you can find in the link at the top of the slide. Those are the complete formal definitions, though. Today I'm going to describe it somewhat less formally in a way that I hope is easy to understand. Constraint type inference deduces type arguments from type parameter constraints, hence the name. It's used when one type parameter has a constraint defined in terms of another type parameter. When the type argument of one of those type parameters is known, the constraint is used to infer the type argument of the other one. The simplest and by far the most common case of constraint type inference uses a constraint of the form tilde type for some type, where that type is written using other type parameters. We can see this in the scale example. S, the type parameter s, has the form tilde followed by a type written in terms of other type parameters, in this case the type parameter e. Since s is written in terms of e, if we know the type argument for s, we can infer the type argument for e. S must be a slice type, and e is the element type of that slice. So let's put it all together. In the call to scale, p is a point whose underlying type is slice int32. Function argument type inference uses the argument lowercase s to infer that the type argument for uppercase s is point. That matches the tilde slice e. Remember that tilde slice e means that the type argument can be anything whose underlying type is a slice of some element type. In this example, the untyped constant 2 doesn't tell us anything using function argument type inference. So the compiler then applies constraint type inference. Since S, we know, is point, and point's underlying type is slice of int32, E is inferred to be int32. The compiler does have to then verify that int32 satisfies E's constraint, which it does, since int32 is an integer type. Now, all the type arguments have been successfully inferred, so the function can be instantiated and called with no explicit type arguments required at the call site. That was just an introduction to constraint type inference and why and how you might want to use it. As I said before, for full details, see the generic proposal or the soon-to-come updates to the language spec. For the final part of our joint talk, I'm not going to discuss what generics are or how to use them, but rather when to use generics and when not to use them. To be clear, this portion will provide general guidelines, not hard and fast rules. Use your own judgment. But if you aren't sure, I suggest that you use the guidelines I'm going to discuss now. Let's start with a general guideline for programming in Go. Write Go programs by writing code, not by defining types. When it comes to generics, if you start writing your program by defining new type parameter constraints, you're probably on the wrong path. Start by writing functions. It's easy to add type parameters later when it's clear that they'll be useful. That said, let's look at cases where they are useful. One case where type parameters can be useful is when writing functions that operate on the special types that are defined by the language, slices, maps, channels. If a function has parameters with those types, and the function code doesn't make any particular assumptions about the element types, then it may be useful to use a type parameter. For example, a function that returns a slice of all the keys in a map of any type, any map type. The code wouldn't assume anything about the map key type. That makes it a good candidate for using type parameters. The alternative to using type parameters for this kind of function is typically to use reflection, but that's a more awkward programming model. It's not statically type checked. It's often slower as well. Another case where type parameters can be useful is for general purpose data structures. By a general purpose data structure, I mean a data structure like a slice or a map, but one that's not already built into the language. For example, a linked list or a binary tree. Today, programs that need such data structures write them with a specific element type, or else they use an interface type. Replacing a specific element type with a type parameter can produce a more general data structure that can be used in other parts of the program, or perhaps by other programs. Replacing an interface type with a type parameter can often permit the data to be stored more efficiently. In some cases, using a type parameter instead of an interface type can mean code can avoid type assertions and can instead be fully type checked at compile time. For example, here's what a binary tree data structure might look like using type parameters. Each leaf node in the tree contains a value of the type parameter t. When the tree is instantiated with a particular type argument, values of that type argument will be stored directly in the leaf nodes. They will not be stored as interface types. Here we can see a method on the generic binary tree. Don't worry about the details or the formatting I used to fit the code onto the slide. The point is that this is a reasonable use of type parameters because the tree data structure, and even the code in this method, is largely independent of the element type t. The data structure does need to know how to compare values of the element type t, and in this method it uses a passed-in comparison function to do that. You can see that on the fourth line in the call to bt.comp. Other than that, type parameter doesn't really matter at all. That binary tree example illustrates another general guideline. When you need something like a comparison function, prefer to use a function rather than a method. We could have defined the tree type such that the element type is required to have a compare or a less method. This would be done by writing a constraint that requires a compare or less method, using the kind of constraint as interface writing that Robert described earlier. And it would mean that any type argument used to instantiate the tree would need to have that method. But that would mean that anybody who wants to use tree with a simple data type, like int, would have to define their own int type and write their own compare method. If we define tree to take a function, as we did in the example code we just saw, then it's easy to pass the desired comparison function. And if the element type happens to already have a compare method, we can simply pass a method expression like element type.compare as the comparison function. To put it another way, it's much simpler to turn a method into a function than it is to add a method to a type. So for general purpose data types, prefer a function rather than writing a constraint that requires a method. Another case where type parameters can be useful is when different types need to implement some common method and the implementation for the different types all looks the same. For example, consider the standard library's sort.interface. It requires that a type implement 3 methods, len, swap, and less. This example shows slicefun, a generic type that implements sort.interface for any slice type. For any slice type, the len and swap methods are exactly the same. The less method requires a comparison, which is the fun part of the name slicefun. As with the earlier tree example, we will pass in a function when we create a slicefun. And this code shows how slicefun is used to sort any slice using a comparison function. Here we use type parameters to implement the sort.interface methods for any slice type. Using type parameters is appropriate for this kind of example because the methods look exactly the same for all slice types. At this point, I should mention that Go 119, not 118, but 119 will probably have a generic function to sort a slice using a comparison function. And that generic function will probably not be implemented using sort.interface. But the general point is still true, even if this specific example will most likely not be useful in the future. It's reasonable to use type parameters when you need to implement methods that look the same for all the relevant types. Now let's talk about the other side of the equation. When should we not use generics? Well, Go has interface types. Interface types permit a kind of generic programming. For example, the widely used io.reader interface provides a general mechanism for reading data from any value that contains information, such as a file, or that produces information, such as a random number generator. If all you need to do with the value of some type is call a method on that value, use an interface type, not a type parameter. io.reader is easy to read, it's efficient, it's effective. There's no need to use a type parameter to read data from a value by calling the read method. For example, some people might be tempted to change the first function signature here that just uses an interface type into the second version that uses a type parameter. Don't do this. Omitting the type parameter makes the function easier to write, easier to read, and it turns out the execution time will most likely be exactly the same for both versions. Going back to the choice between type parameters and interface types, when there is a common method that is used by different types, consider how that method is implemented. Earlier we said that if the implementation of the method is the same for all types, go ahead and use a type parameter. Inversely, if the implementation is different for each type, use different methods. Don't use a type parameter. For example, the implementation of read from a file is nothing like the implementation of read from a random number generator. That means that we write 2 different read methods, and neither method should use a type parameter. Although I haven't talked about it too much today, Go also has reflection. Reflection permits a kind of generic programming in that it permits you to write code that works with any type. If some operation has to support even types that don't have methods, so that you can't use an interface type, and if the operation is different for each type, so type parameters aren't that helpful, use reflection. An example of this is the encoding JSON package in the standard library. We don't want to require every type that we encode to support a Marshall JSON method, so we can't use interface types. But encoding an integer type is really nothing like encoding a struct type, so we shouldn't use type parameters. Instead, the package uses reflection. The code's too complicated to show here today, but take a look at the package if you're interested. In closing, this discussion of when to use generics can be reduced to one simple guideline. If you find yourself writing the exact same code multiple times, where the only difference between the copies is that the code uses different types, consider whether you can use a type parameter. Another way to say this is that you should avoid type parameters until you notice you're about to write the exact same code multiple times. Thanks for listening. I hope you've learned something today. I hope you'll all be able to use generics in Go. I hope you will all use generics in Go when the 118 release comes out. I hope you use them wisely and well. Thanks.